This video is going to look at nonlinear models and take a particular emphasis on exponential models. Now, nonlinear models, there are plenty of them that exist, so please do not think that nonlinear models are only exponential models. They are the only type of model that will be focused on in this video. Alright, so previously, if you've studied some modeling, linear models assume that you are changing at either 0 or a constant rate of change. So you're either going up or down by the same amount over each period of the independent variable. Now, nonlinear models, that is not the case. It may be 0 for a little bit. It may go the rate of change may be increasing over time, it may be decreasing over time, it may do both over time. We don't know. Okay, so nonlinear models encompass all those different scenarios. Okay, so again, this video is going to focus on exponential models. We are going to focus on one particular example in this video. So let's assume that we have an apple gram core. They're typically about 100 grams. There's a little bit more on this one, so there's 110 gram apple core. It's discarded in compost pile, and it decays a little bit each day, losing 25% of the mass from the previous day per day. Okay, so each day is losing 25% of the previous day's mass. Okay, so in other words, if we have 110 grams for the mass of the apple on day 0 when we initially start the study, the next day it's going to lose 25% of that, so 110. Another way of framing it is it retains 75%. Okay, so I'm going to look at it in that light too. You can certainly do the 25% and subtract it off. You will get the same answer. So I'm going to multiply this by 75%. So as a decimal, that's 0.75, sorry. And that ends up being 82.5. Okay, and then to get day 2, you would say, okay, well, it still retains 75%, so you would take 75% of this, so 82.5 times 0.75, that's a decimal, and you end up getting 61.88 if you round. Okay, and then day 3 you can do the same calculation, or the same type of calculation, and get 46.4. Okay, these are all in grams. Okay, so based on 5 days, based on the pattern, you can continue this for 5 days. So at day 5, you end up getting 26.10 grams. Okay, please feel free to confirm this by pausing the video. Okay, part C says, okay, graph the data. Okay, so I'm going to open up Excel, and we're going to pretend that this information is not there. And for day 1, we can set up a formula, and then hopefully it'll apply for the rest of the days. But again, what we would do is we would take 75%, so 75% times the amount that existed previously. So that's available by clicking on the mass corresponding to day 0 in Excel, and we get 82.5. Go ahead and drag this down for, I did it up to 10 days. But you can drag that formula down or repeat that formula by, again, taking your cursor, hovering over the lower right corner where there's a little box until your cursor changes into a black cross, and drag that down. And you get the different values. And if we want to graph this data, all we have to do is select all the data that we wish to graph, go into Insert, and I'm going to make a scatter plot just because I have discrete data, okay, and we can see the trend here, okay. So then the question was, what type of model works the best here? Well, if we had a linear model, what we would see is from this initial point, from 110 grams, we would see some sort of straight line occurring. That is not the case. We're seeing something that is not changing over time, or not changing at the same rate over time. So it decreases quickly and a little less quickly over each time period. So it's decreasing at a decreasing rate. Okay, and that is indicative of a exponential model. Okay, so probably an exponential model. Okay, exponentials either increase at increasing rates or decrease at decreasing rates. Okay, and you will get some more practice with all this as you continue on. Okay, so part D says determine a mathematical equation or a model that describes the change in the mass of an apple. Now change, we can either do delta or prime notation. Okay, so well, I'm going to probably stick with prime for right now because we're thinking of it as it's changing right at a specific moment. And so if I say let m be I'm going to say m of t. This is going to be the mass of the apple core on day t. Okay, so if I look at the rate of change of the mass of the apple, I denote that by m prime. Okay, and I'm going to add an extra little bit here of t just to denote that I am looking for the rate of change of the mass of the apple on day t. Okay, so all this means is on day t. Okay. The information given to us in the problem says that it decreases, so a decrease is denoted by a negative sign. It decreases by 25% of the mass of the apple from the previous day. Okay, so the t minus 1 is the day before day t. Okay, so this here is the equation that I want. Okay, so again, it loses, okay, so it loses or it decreases by 25% of the mass on day t minus 1. Okay, and then part E says write an equation that describes the mass of the apple t days after it is first discarded. Now the mass of the apple t days, well, that's m of t. Okay, so the mass of the apple on day t. Okay, so what we have to do is a basic exponential model is either of the form a of t is equal to a naught e to the kt, or one that's even more broad is a of t is equal to a naught, and then I'm going to write b to the t. Okay, and b, so a naught in both equations is initial amount. Okay, now the difference between the two models, this one you can actually obtain this second model from this first model through some simplification, but this first one typically deals with quantities that decay at a natural rate. So since E is the natural number, we're talking about quantities like radioactive materials that decay at a certain rate, or other values that have a rate constant, because K is called the rate constant. Okay. And then B here is just some base. So for example here, if we work strictly with this second model, A naught, we know the apple core begins with a mass of 110. Then each day we need to go back. I want to go back to our table for a minute. And each day we know it decays by 25% or it retains 75%. So notice that in the table, each day I'm multiplying by 0.75. So what this ends up being is that to obtain the mass on day t, you need to multiply by 0.75 some number of times. So the mass on day 0 was 110, so I'd have to multiply by 0.75 no times. But when I do it as an exponential, if I have t as 0, it will be this quantity will be 1, so I'll just get 110. To get the next day, I would have to multiply by 0.75, which would allow me to get the value observed on day 1. Okay, so exponential model can follow either of these forms. In this case, we chose to follow the second one because we're multiplying the mass by 0.75 each day to progress in the table.